So this is about what I have been doing, for the past few years, and now I would like to switch over to like a more talk kind of a thing where I'll tell you what I know about, say, this field of autonomous vehicle. So, as most of you might know, this all started in say 1985, 1987 with the Prometheus project in Europe, and then the Beta 2 by Jain was a car, the right side here, which was already driving successfully on highways for significant intervals of time. And finally, it all came together in the first DARPA challenge, where I mean the interesting part here is that all teams failed to finish this 150-mile off-road run. This was because the requirement was that everything has to be fully automatic and nobody can take control over the vehicle. But then this changed in 2005. So the similar challenge happened in 2005, and this time 5 teams managed to complete the off-road run without much human intervention, without any human intervention. And Velodyne, it was then a startup. This is where Velodyne, I think, came up. So Velodyne is a LiDAR company. They were a supplier to all these teams. There was also an urban challenge in 2007 where they modeled the test environment close to a typical urban scene. But then, of course, it was not dynamic, it was static. We didn't have the pedestrians, we didn't have a lot of issues that we have in. Now, there are essentially 2 ways of doing, say, autonomous vehicle. One is, say, the end-to-end approach. And in this end-to-end approach, what we are saying is, we'll just have, say, a giant black box, maybe a neural network, and we will give it all inputs that it needs. For example, the camera video and the GPS location. And what it should do, it should directly give us driving commands. How much to steer the steering wheel, how much to press the brake, or get to the radio. So this is one way of doing it. I'll tell you about pros and cons of this approach later. And the other, more standard way of doing it is the modular system. And in modular systems, you have essentially these steps: perception, scene representation and localization, prediction, planning and decision making, and vehicle control. So I'll go over all these steps in a few minutes, maybe 7 to 10 minutes, and then we'll talk about it. So what is perception? Essentially means the ability to see, hear, or become aware of something through our senses. So for a robot, perception means, for example, in the context of, say, an automated vehicle, it needs to know about the various moving objects that there might be. So these moving cars, the train, all the static objects, such as these traffic cones, road signs, so not just detection, but also recognizing what road signs they are, overhead signs, traffic lights and their state, is it red, green, yellow, lane lines, solid white line, double yellow line, and so on, because a lot of them have different meanings. You can overtake, road markings, there is halt, or it could say school again. Curves, because curves are where the most important objects humans walk. Similarly, crosswalks, also environment tags, like maybe to work with a residential area, a tunnel, or we're approaching a road. So this is all perception. We need to know all this before we can move on to the next step for this model. Now let's talk about, say, just one category of all this. Let's just say moving objects, right? So moving objects can be of so many different kinds. It could be a cycle, a human, a person, a bicycle. It could also be moving objects in different states. For example, objects which are met with a collision. For example, on the truck, which was a moving object, is no longer moving. You also need to know additional subtasks. For example, the state of the blinkers, the indicators, the parking lights, is it under collision, etc. So moving objects themselves is very different and very diverse. And let's just say, we are talking about only one kind of moving object, let's say car, but the car also can look very, very different based on the situation. And finally, what we want norm is not a 97% accuracy. Finally, after all the steps, it has to be this sigma accuracy, only then it's qualified to be whatever. Now, the biggest problem with perception is the long tail problem. And the long tail problem essentially means that we want to capture the qualitative, but those by definition do not have so much in training data. For example, if you want to say understand the human driving behavior, so some very few of them are conservative, very few of them are aggressive, but the majority of them fall around the mean, which is like average driving, right? So then the long tail is basically the conservative or the aggressive which we are interested in, but they don't occur so much in data, right? But that is what we want to solve. So this is probably, in my opinion, one of the world's most advanced the Skydio 2 class. And for them, this is from their website. These are the tail cases, right? So Skydio cannot work when there are, I mean, they say that you should not use it when there are moving objects or cars. I'll tell you later why. So in low light or extreme sunlight, it doesn't work for obvious reasons. And also for around reflective surfaces, still water mirrors, and small obstacles like hindrances, utility lines, ropes, chain link fencing, etc. So this is something that we need to somehow work with. Now this is like 1 in a million data point, right? Where you have motorcycle coming in from somewhere, then collides with a trailer. Luckily, nobody was harmed or hurt in this video, but it takes maybe 1 million miles of driving to get one such data. Let's now talk about, say, probably the simplest object category on the road, which is the traffic sign, because traffic sign is a 2D planar object. It's it's the most it's the simplest object. But the challenge is when you want to solve, let's say, traffic sign detection and recognition, is that it has to have a very high accuracy. And in Germany, there are more than 600 classes of traffic. It should work without HD maps, and there's a huge data imbalance. Some rare signs, which are still very important, have only a handful of examples. There are also text-only signs, especially in the US. So your system has to work also on signs where there is a written text. And finally, we need to build a low latency, high accuracy system because here we want to then. So here the goal is not autonomous driving, but say L2, L3, level 3, or kind of thing where you simply show the sign, the detected sign, into the driver's dashboard so that he or she is aware of what sign are they approaching. Now, even to build such a simple traffic sign recognition system, when you want to do it in practice, it involves all these steps, right? Because there are 600 classes, you cannot use your detector to give out all those 600 classes to start with. You come up with, say, lesser number of classes. Then there is scaling and cropping of that object of interest, which goes into the second level classifier, the 3232 classifier. At the same time, the traffic sign detector is put into an OCR block, which reads the text, and then it gets processed into semantic meanings. And finally, traffic sign need to, traffic signs can occur as a group, and they need to be understood with their parent association. Sometimes the meaning of the traffic sign can change based on what it is occurring with. So all this has to be done even for the simplest traffic sign recognition problem. And then you have to deal with these kind of cases, right? So this is again a tail. So we've now done perception. So we now we understand the world. We know what occurs where in the image or in the 3D. Now, after we do that, we need to accurately localize ourselves in this world, right? So the most accurate way of doing it is to first build an HD map, a very high resolution 3D point cloud of, say, the area that you're interested in, and then based on your current measurement, you try and place yourself in this 3D map, right? So you know that based on your rough GPS location, you are in this vicinity, then you do some kind of algorithm, say like it is closest point, and based on that, you match this partial observation that you currently have to the SC map that you collected previously, and you can localize yourself very accurately in that pool. You can also try to do it without, say, like our 3D measurement, for example, what Tesla was doing, and here you have to do it using only vision. So after you've done this thing representation and localization for the scene in the bottom row, you will essentially have this understanding, right? You will know where you are, where the car is. This yellow box is this pedestrian. Those purple boxes are essentially vehicles. You know the speed limit. You know this is the yield sign because you recognize it. You know that there is an intersection. The state of the line is green. So this is how you then represent the the word that comes from perception infusion into what you what the computer basically see. Now you've done perception and you've localized yourself and others in this common 3D. Then we need to do prediction. So we need to predict where others will be. And this is because suppose we are on a highway, right? So we don't have enough time to make the maneuver if we do not predict where others will be. For example, and also on a highway, prediction is somewhat easy, right? Because the car has a very well-defined behavior and it will not divert from that behavior very easily. So it's easy to predict what the car will do, say, a few milliseconds in the future. So in this case, we're trying to predict what the bicyclist will do, and it's predicting that it will stop at the traffic light. So once we predict what others will do, we then decide on what we should be doing. Okay? But prediction, even though it sounds very simple, you could maybe just like if you were just simply forecasting. You see that Cruise recently met with an accident late last year, and the user was that Cruise was actually making a left and stop at the intersection, taking an oncoming vehicle would come in front of it, meaning it got this prediction wrong. Right? So prediction is also very important. We also sometimes need to do prediction in the sun, especially for fixed wings, which cannot change their course so easily. So this is by zip line in Africa. In Africa, they have certain challenges. For example, the AEC is not always aware of all aircraft flying. So this is an acoustic phase obstacle avoidance system where this aircraft, the red one, and acoustic sensors, and based on this, it can localize objects which are emitting certain, say, numbers. For example, these bigger airplanes, which they are interested in avoiding. And finally, planning and decision making. So once we've perceived, we've localized ourselves, we've predicted where others will be. Now we are in a state to plan and decide where we should be going. Right? So if we know that there is a traffic flow and the green Jeep will be at that point, we then have a search algorithm where we come up with different paths. All each of these paths can be associated with a cost based on our goal, what we're trying to achieve, right? And we then choose one of those. So this is final planning. So you also do that for the drone. This is an indoor space where the drone is trying to enter the other group. And since this is in the outdoor setting where we're again trying to, so this is a given waveform, but then because there is an obstacle, it then needs to replan and go around the obstacle. Finally, we need to then execute the path from motion planning by giving it relevant actuator commands, how much of the steering to turn, how much of the brake to push, right? There are errors all the way because we have not modeled the physics 100% perfect. So we then have to somehow fix those control errors, how to translate what we want in terms of motion planning, the manual control by the actuators. So modular versus end-to-end. So what is the advantage of doing modular architecture? The biggest advantage is that it helps are divided tasks within a team. And engineering is made easier, more interpretable. You can add hand-coded trials easier to each module. But each step, I mean, the forms are that each step of the process is performed in sequential modular silos. That has to be manually tuned for each introduced change. Limited information is shared across modules, so there is a cascaded error. Whenever there is an error early on, there is no possibility for a future module to fix that error. And finally, rely on modules to each problem. For example, say fix a foliage problem, which is a very well-known problem. Autonomous driving, where there is foliage in front of the traffic sign, you need to do something very specific to solve that problem. And then you keep doing that for your entire long period. Now, the exact opposite approach to doing this modular way of doing things is this end-to-end, where we're saying, okay, let's just replace all of this with a giant neural network. So the advantage is that, of course, it's a single AI system, and it is really trained for the end task, what we're trying to optimize on. But it is difficult to add trials and rules. It lacks interpretability for validation and safety, and requires a lot of examples because I have this huge network doing everything into it. However, this is work from Wave, based out of Cambridge, UK, where they are trying to do this end-to-end. They have achieved certain amount of success. Their claim is that they will probably not be the first one to get their cars on the road, but they will be the first ones to save 200 cities. Let's see. So this is essentially an influence to what they have, and you have your input, which is of the view of your dimensions given how big these dimensions are. Other say measurements are. You then put this into a network, and the network has to give you say 10 outputs based on the actuator or other ways of control. Should it bring the indicator and so on. And then they're trying to interpret some of the intermediate representations learned by the network in terms of attention, uncertainty, semantics, geometry. So one very interesting thing that came out was attention. So they have this end-to-end transformer for driving on, and this was something learned, implicitly, not explicitly. So what is interesting to note here is that the attention of the model changes from the traffic light to the road when it turns from red to green. So once it's green, it's no longer looking at the traffic light, and this emergent behavior. So these are ways with which we can try and interpret, but you can already see that it's not very straightforward. You need to do something extra to then interpret what the model is. Probably the best of both worlds is the middle part. So hybrid approaches. So it's joint perception and prediction, meaning what they're saying is, you basically do all the way till prediction in the first network, and then do everything else the way you were using it. And here, one way to do it is to say predict the occupancy map after forecasting. So you have your current occupancy map, you predict where others will be, and based on that you predict your future occupancy. Okay? And this is what Wabi is trying to do. So Professor Urtasun from Montreal, she started this company, they $1 million recently, and yeah, they recently partnered with Bhopal, and these are some companies that I'm tracking, which I think are doing very good work. Now, the difference, between classical and modern ML systems is earlier. We all had access to these simple tools, and with these simple tools, we could build simple things. But today, if you want to build these large-scale models trained on this big data, you need to build, say, a factory. So building this factory takes time, but once you have this factory built, you can find a lot of things through this factory. And what does this factory look like? Well, this factory looks like something like this. So you start with a little bit of data. Right? And data is usually noisy, especially when analyzed by humans. So the way we do things is we curate some data, we know somehow manually maybe the developer themselves select say 100 examples from each class, train a very initial model and deploy it. Once deployed, we then try and find inaccuracies in the system. Of course, there is no ground truth, but there are still ways to find inaccuracies, right? So, for example, we find that the car is maybe not doing as well inside a car. Now, how do you find these inaccuracies? There could be many ways. For example, one could be driver engagement. If the driver is having to take over from the autopilot, then that means that this is an interesting piece of data that I should maybe send that. The other is say tracking errors. If it's very jittery, tracking fails, that is something that could be interesting. Thirdly, it could be mismatch between different sensors. The left sensor is seeing something else, but the RGB or the LiDAR is seeing something else. And then finally, uncertainty measures. For example, you have a bunch of different models on your data, and then if the variance is large, means that high uncertainty, that would mean that this is something that you can take back. Put it in your data, get it labeled, and then put it back into your training set, retrain your model, and then keep doing this again. This is not just true for autonomous driving, but any system. So if you work with toy data sets, academic data sets, this is not a problem. But if you have a data labeling company that you're working with, then this is something real that you need to do to get your model to the kind of accuracies you want, and also to inform the data team how and what they should be doing, because they did not get it right the first time. Sensors, so sensors of course are super important, but then what we want in sensors is to have complementary and redundant systems. So different sensors have different properties. Redundancy is good because they can be used for payload, for a payload. And then it's also very important to have redundancy. And Boeing 737 MAX, as we all know, is all these unfortunate accidents happen. This is simply because the angle of attack sensors did not have proper redundancy. So the angle of attack sensor is essentially, so let me not go into what happened. But let me tell you, so there's this interesting documentary for people who are interested to look at what happened with the redundancy and why it failed. But the summary of the FAA's review from 2020, essentially all they had to do, so they did have redundant sensors, but their software had not. So whichever sensor was firing, they were just directly taking that sensor measurement and controlling the plane based on it, especially in the system. Right? So now all they have to do is, if the difference between the angle of attack inputs is above a calculated threshold, F60 will disable the SCS, including the NCAPS function, for the remainder of the flight and provide a corresponding indication of such a deviation on a flight there. So the human could take over instead of doing something wrong repeatedly. This is again some measurements that we did in terms of the various sensors by different cars at the time. And what we found was that the Tesla is probably the most unreliable one, because they also need a cost that they need to be under, because they're selling it to consumers. And it is reliable enough environmental perception only for standard driving use case. Most modern cases not manageable or with severe restriction and no redundancy. Google was very good in the near field due to the availability of, say, the custom LiDAR developed by Google for this near field, and over XC90 had obvious problems which it was related. We did similarly for various aerial vehicles before we started tailored 1.0. We currently have 2 depth sensors, 1 tracking camera, iris camera, and single point line. Now, because of this long tail, simulation is super essential. So simulation can give you a lot of things. This is our own in-house simulator where we use SN and Unreal to. So now in the simulator, you can say, you want snow, rain, and you can apply them on. You want leaves, and then the flight dynamics also change. Hardware in the book where you connect your flight controller to your simulator. So all that changes is your actuator and sensor sensor measurements. Your sensor measurements are now coming from the simulator, and the actuator commands are again going back to the simulator instead of the real hardware. And this is super important, not just for the algorithm. Of course, you need to first test the algorithm so that there's not a collision about the algorithm. We need to test if that is correct, right? Find out this path. So this is one way of testing it. Secondly, it's also useful for say first time flyers because the flight dynamics really change with all this, and especially if you want to learn how to fly, say, PV or first person viewing one where it was forward. So they're super fast. So how do you learn to fly them, right? You cannot afford to maybe crash them. So one way to do it is using a simulator. Simulation, of course, is a lot of everyone is doing it. Google is doing, or rather was doing 10,000 miles per day. They had more than 7 million miles at the time, and there were also newer approaches to do the simulation. For example, this work again by Professor Systems Group, where they try and render it back all the way to the sensor. So you may not always use the simulator to render it back to the sensor. You may not use it for perception, but for everything after that, everyone uses simulators. But here the trying to use also for perception, where they try and render it. So you have the scatter model on the left, this like card, and then it gets rendered. Looks pretty realistic. You need test facilities, whether you're doing cars or aerial vehicles. So Bio has this 91 acres in Castle, California. Now, so let's quickly talk about. So this is all that I had for previous topics. Now let's quickly talk about a little bit about say testing these systems. So one way to measure the this is called semantic segmentation, where what we need to do is given an input image such as the water, we need to find a label for every pixel. For example, here cars are labeled blue, the road is labeled purple, the trees are labeled green, the sky is labeled blue, and so on. Right? So this is semantic segmentation. Semantic segmentation, the performance is measured. One way to measure performance is sort of mean average precision. Mean average precision essentially is the mean over all classes of average precision. Average precision is the average precision over, so it's converted into an application problem, and then we simply measure this performance. But now, what is a good metric? What is a good MAP score for a car to be, led by another road? There's no clear answer. Also, consider MAP for semantic segmentation. No specific, so there's no specific threshold. And the score can change. For example, for the overhead wire, right? In the top image, the overhead wire was predicted. But in the bottom image, the cyclist on that island, right, the right side, is not predicted. But both of them have the same MAP score because the same amount of pixels are essentially predicted. So that because it's an average end of the day. So this is clearly something which is, that can cause problems because if you set the threshold for an MAP score, it can lead to problems like this. So testing essentially is not very direct. Also, what kind of a recall you think is good enough? For example, 96.6 recall for cars is good enough. These are results from the public leaderboard, the kitty leaderboard for 3D object detection. And you can see that it even struggles with easy cases. So what we want is at least 100% recall, but this is clearly not happening even for the best models on the leaderboard. And it is hard to decide on exact expectations of precision and recall. So one approach that we are doing is, it's called, say, we call it unit test or other common sense unit test. So what we're saying is that at least for also the blue, signifies cars. And what you're saying is at least where there is, all this yellow area, we want 100% recall, meaning all this area should be marked as this car fixed. Now, the initial model, you get these gaps. So this part of the car on the left, right, this one, it doesn't get labeled as a car. So this is clearly a problem. So the red areas are essentially areas where our model will say this test. Right? So this is one sanity test which we take into our models. Similarly, you can do it for other classes, for example, the car, but also the road. You can also have tight or loose test, for example, on the left is loose, it gets tighter and tighter, right? So the absent and present polygon. So the yellow is essentially where nothing is something is present. Purple is where nothing is absent. Now it predicts something is present in the purple region. Then we have a problem. Or if it predicts that there is nothing in the yellow region, then there is a problem. And this can be obtained easily, for example, using these coarse annotations either already present in datasets such as city states, or while annotating our semantic segmentation, we can also ask the labeling team to do a course level loose, let's say, which we will use in our. We can also extend this to 3D, so presence and or absence of 3D polygons instead of these polygons. And like Professor Philip already covered, like hardware is a big deal because you have so many sensors and you need to run all of them in real time without enough latency. So yeah, hardware is exciting to start very well in the morning. So skip this. Now there are tons of companies trying to do it. I was very happy to work with a few because with Apple as a researcher and then with all these companies as well. Yeah, and let's skip a little bit of autonomy. I'll basically want to, so this is the last topic that I'm going to cover. I want to use, so there's a lot of time press, especially for autonomous driving. But I'm going to show you how far we have come. And in the next slide, I'll also show you what is the positive that has come out from this initiative instead of just looking at the negatives. Right, so this is, I think, the Phoenix. This is another situation. It's a very tricky situation where this car, there are bike which comes suddenly in front of the car, and then it has to also go through this crowded scene. There will be car coming from the opposite direction, but we're able to do all this very. This is again close. Now again, there will be a tricky situation. After it crosses the first intersection, where there will be a bicyclist again coming out from nowhere, and the car handles it very well, maybe better than I would have as a human driver. So you see, so stops patiently, go and it's all smooth. So this is already things that are good. Now, Oliver, the VP product Cruise, said it took them 7 years to unlock one car, but in the last 12 months, they've unlocked 125, scaling 173. And what he thinks is, R&D is no longer a limitation. Of course, they're spending heavily on R&D and there are a lot of interesting things coming out, but the R&D is solid, right? It's easy. So that's at least what Cruise thinks. So yeah, of course, the batteries, right? So with all these incidents, especially Tesla, where were delivering more than what they have, and then under delivering their practices. But the positive of this is that the automatic emergency braking standard now, which is a part of every car from September 2022 in America, was say culmination of an agreement and a voluntary agreement between the automakers, the insurance institute, and the National Highway Traffic Safety Administration. So now all cars in America will have this emergency braking as a standard. And what this insurance institute, private institute has found is that radar or camera link brakes have cut police reported rear end collisions by 50%. So in my opinion, that's a huge number, right? If you can reduce the number of rear end collisions by 50%, I think you've done something right. Similarly, automatic braking has reduced the number of car during collisions again by 30% based on police and insurance data. And finally, anti-lock brakes, cameras, radar, ultrasonic sensors will manage and ultrasonic sensors to manage blind spot and lane departure monitors and adaptive cruise control have become a standard or are becoming one very quickly. Now, this $1 million question: when did we have good autonomous starts? Good autonomous meaning level 5, like us humans. So if you simply extrapolate this curve, so on y-axis we have number of miles, and on the x-axis is the year. So automated driving till 2020 was doing about say 10 to the power 4 miles. Without disengagement, humans do about 10 to the power 8 without the first accident. So if you simply just extrapolate, this would be 2037 for L5 level autonomy. But this is just extrapolation, and I hope we'll do it. But we're doing level 4, where it's a known environment, right? It's a geographic area where you want to travel, and that has already come in certain parts of San Francisco and Phoenix and other areas, and more of that will go. In fact, I believe that maybe the level 5 is something that we don't need. Level 4, and then simply extending level 4. The perimeter of level 4 is what we will get in the next year. And a case for India, so this is when I was at IT having a coffee in Hiranandani and it's on the street where the traffic police is trying to, manage these pedestrians, these bikers, these cars around this circle, and then so many things are happening. So, I mean, when will we get there is the question, right? So there are some startups in India who are trying to stay in this direction, and it's a joke, but maybe it's even easier to do it in India. We don't need to do traffic sign recognition, lane detection, light detection, right? And our speeds are low, maybe it's not so hard here. We should try to. And people like Autonomy is now so something in this direction. So there is a car, which is a collaboration with Intel, which already has a lot of sensors, LiDAR, other sensors. Companies can request to the car for data collection purposes if interested. And yeah, so this is all I have for you. Thank you so much for your time.
Thank you, Arjun, for a really stimulating. Thank you, Arjun, for a really stimulating talk that showcases how deep tech can be used for complex applications. I'm sure our audience then would be similar to ask your questions. So to catalyze that, there is some of my own questions. I showed these different protocols running the modular based protocols end-to-end machine. Now, if you look at the explain it's two different versions. It will probably be better the modular one and make end-to-end. So regulators say that you shouldn't use a modular rather than this because of the explainability of systems.
Yeah, absolutely. So explainability is definitely very hard when you monolithic network, and it is much easier when you have this modular thing where you can explain the output of every module. But yeah, so this is why most people are doing modular approaches. People succeed at euros, YMO, etc. Everybody is doing modular approach. But there are some interesting aspects of this end-to-end approach which will probably get involved.
Hello, sir. Thank you for this interesting talk. I have actually two questions. The first one is related to that basic perception problem that you said. In which the problem was that there are few rare signals which were and the data set will be there to find in the training data set, right? So can it be solved using data augmentation techniques like use some better simulator like
Yeah, sure. So data augmentation, you use it for balancing your class, but yeah, the really, sure. So data augmentation, getting synthetic data, using simulators, getting photorealistic images, all that is something that is okay. But the simulator itself has limitations. How is the simulator function? How do you create the world inside the simulator? So that is also done based on, say, data or human, say, an artist or human labor. So if you can create those things, yeah, but it's a chicken and egg problem.
The second question is related to the end-to-end learning, where there was a given network and you try to predict the future state of the vehicle with the use of spirit. So I was really confused and I couldn't understand that how, like, let's suppose a car is taking a left turn. It has to predict that it has to put on the indicator as well as turn the steering, as well as slow down its speed, and then do all these things that at a single stage. How is it predicting all these states at once? Only one with the use of only one.
Not only one output, there are 10 outputs. So the outputs could be, should you start your left indicator or right? What should be the differential in your steering wheel angle, your gas, your brake effect. So you're predicting all these controls, not just hardware. So you're predicting all of these, and then you're giving it to the vehicle.
Thank you, thank you.
I have a question about car design and road network design, which both assume a human driver right now. So can you comment a little bit on that? Moving on.
Yeah, that's a great question. So, I mean, why is the autonomous driving so hard? Because we're trying to retrofit these autonomous vehicles for roads and infrastructure designed for humans with eyes and ears, right? If we were to do it, for example, Professor Suresh Sundaram did it for NTU Singapore, and what he did was he put magnets in the center of the room. So with these magnets, you can have, so these are essentially passive, you can have passive system with which would accurately relocalize your car when you go over these magnets. So if you do such changes to infrastructure, our problem becomes significantly simpler. But since this is something we don't want to do, maybe, or if you do it for, say, new campuses and smart cities that are being very, but currently not that is happening, and we would want our cars, these enormous cars, to do more than just what is happening. So yeah, I agree with you. If infrastructure could change even slightly, then our problem will become very.
The different what if everything that you presented comes from the sensors of the car itself. If we have well-behaving cars, and they communicate with everyone's sensors into the network, could we improve the statistics and this?
A great question. So GM started this initiative. It's called V2X or something. And in their high-end cars, their in the company, but the high-end cars, they have this, and they can talk to GM cars. Now it helps with the rear intuition on highways, but then it's again like bringing people together because now they can only talk to GM cars. They cannot talk to say Ford or Tesla yet. So it's already out there and they're talking to each other, but not to other companies. So the impact is.
But there is improvement. Right?
Yeah, yes, that's true.
Thank you so much for the great talk. My question would be related to the case for India, because we in India, instead of preferring traffic signs, we prefer कि अगर सुरक्षित जीवन चाहिए तो गाड़ी धीरे चलाए. These type of traffic signs are used in India. So how the cars will be able to recognize such traffic signs in India? And we have seen that the formal traffic signs from the foreign countries are scattered away, like you'll find a 10-mile speed limit here and just 50 meters up, far you will find a 20-mile speed limit. So how the model will be able to interpret all these traffic signs?
So, a two-part question. I mean, I didn't understand your first part. Are you saying that how do you do it in India? And then secondly, what happens when there are two traffic signs, one after the other? Yeah, so if the two traffic signs one after the other, the car starts to behave how it should based on the traffic sign, based on what it has seen first, and then if it seems, then the second one overrides the first one. So that's pretty straightforward. And how do you do it in India? And there are various approaches. So yeah, like I mean, for example, so firstly, people need to be interested and they need to work on this problem. And I know of 200 startups only in India, so as far as robotics and minus zero. But there needs to be a lot more interest and also, people working on it. So also in academia, I don't see too many people really, because so like Hyderabad probably is doing something where they have two cars, one is this one, the others group also have another one. But again, very few institutes where they have an actual car and they're working. So
The year 2037 might be global, but for India it will take more time.
Let's say, I think it's too far in the future for me to.
Thank
Yes. I saw. So I was just wondering, like, what is the state of the art on the moral dilemmas of these? So how do companies tackle this problem these days? These have been a long problem.
Yeah. So yeah, to range tracks and then one having somebody and the other having somebody, but I think we're far away from that currently, but we're not at least. So even before the modern dilemma, they should be able to stop at least, like, so it's not there yet. So this is not stay so much into the foreground here.
So let me comment on companies. Whenever say harm is inevitable, so what is the policy that these companies? So some of them will distribute money. How do they distribute money?
Currently, we're not there where we think about these advanced questions yet. Currently, it's about stopping the car so that the harm is removed. But we're not there where we try and minimize the harm, where we go into the divided systems. It's not there. Thanks for the question.
Yeah, thanks, Arjun. So there is no driver in the seat at all, or there is a driver who can, in case something horrible is going on.
I was talking about the whole gap. So the traffic sign that you were displaying on the dashboard, that's automated driving, maybe level 2, level 3 autonomy, where there is still a driver, but the car can do certain things by itself and then alerts the driver if the car is very uncertain.
Level 5 is
Level 5, we're focusing on level 4, where it's predefined area, and level 4 is where there is no driver.
This is following the conditions question. Suppose an accident happens. This is such so that it makes the legal case situation is set. And how does one prove that it was who's accountable?
Yeah, so firstly, on telemetry data, all logs have to be stored. So, for example, with these investigations, it was found that Tesla was essentially taking off their autopilot just before the collision because they wanted to say that autopilot was wrong. So, like we need to then say all these states, what happened, there are all these sensors that are around the car. So we have a pretty good understanding of what happened in the last moments before the unfortunate collision.
So it's like suppose so am I to blame the engineer developing stuff or am I to blame Tesla? So who is more accountable? That's
Yeah, one question is that, another question is, if you have all the telemetry data, when the algorithm is doing some, who's at fault? I mean, who's going to say that the algorithm really did the right thing?
Yeah, I mean, it's a hard question, but I think only time will tell. There are all these court cases pending in American courts. And based on how they go, they will set precedent and we'll see which way it goes.
Yeah, and so you covered, there are few percentages in place, maybe like city cameras, in certain states, maybe to track and different stores of other cars before your car is that you can access what is the station.
Yeah, sure. I mean, we have an infrastructure, but it's not wide enough for cars because how do you get information from that speed into the car? It's still not allowed.
I think we now have a close session in this maybe I'm sure you can follow Arjun or the feedback and we'll be happy to answer the other questions. So please join me again in thanking all the this of the it's in India, but there is a certificate again for a cheap. Thank you, and now we'll turn to the feedback.